Assalamualaikum warahmatullahi wabarakatuh and good day for all. Today I would like to share a video in chapter 5 of static subject, which is analysis of structure. Before we go through, let's see the content first. We will start from the introduction, definition of truss, simple trusses, analysis of trusses by the method of joint under special loading condition, and we have a space trusses, and there is another method which is a method of section trusses made of several simple trusses. We have analysis of frames, and finally we have machines. Along the way, we will look at the exercises and sample problem. Okay, for this application, basically trusses are commonly used to support a roof from your house, a roof from a auditorium, a roof from the stadium, and many more. So there is a question we need to consider. So for a given truss geometry and load, and how we can determine the forces in the truss member and select their size. And more challenging question is that for a given load, how can we design a trusses geometry to minimize the cost? So trusses are also used in the variety of structure like cranes and the frame of aircraft or space station. So the question is, how can we design a lightweight structure that will meet load, safety, and cost specification? Okay, in this chapter, you will need information in the previous chapter 4. Two information we need to apply from the chapter 4. Number one is a resultant force is equal to 0. And the second one is a couple, which is a moment at the certain point is equal to 0. And we need also to consider this diagram, which is a reaction at support and connection of a two-dimensional structure. Reaction equivalent to a force with known line of action. So we have a roller, rockers, frictionless surface. We have a short cable, short link, and we have collar and frictionless rod, frictionless pin in a slot. So the free body diagram of this reaction at support you need to consider. But in chapter 5, we are asking to determine the force in each member of this structure. So there is a difference between chapter 4 and chapter 5. And also in chapter 4, we are given the center of gravity. But we didn't ask to find the value of this G. So in chapter 6, we will discuss on this. Okay, for the introduction, the equilibrium, which is which can divided into two parts. The first part is structure, and second part is a single rigid body. For the structure, we will go for the internal forces, and then we look at the internal forces. So both two things we can analyze by using different methods. And then we have for single rigid body, we have external forces, which is something like this. Please look at this diagram. For the equilibrium of structure made of several connected parts, okay, which is the first one is internal forces, okay, and the second one we have external forces, which in this diagram indicates 80 kilonewton, and also we have 50 kilonewton. In the interaction between connected parts, Newton's third law states that the force of action and reaction between bodies in contact have the same magnitude, same line of action, and opposite sense. That means opposite direction. So that means in this Newton's third law, we need to utilize the net force is equilibrium to zero, and the additional of moment, which is the equal of moment at a certain point, is equal to zero. So this Bose equation are used to calculate for the exercises, for the problems. The three categories of engineering structure are considered. Okay, the first we need to look at the trusses. The second one is frames. The third one is machines. For the trusses, which is to support loads and usually stationary. So that's mean we have a roof structure, and fully constrained structure formed from two force member, which is straight members with endpoint connections. Later on, we will see these things. Okay, after this, for the frames, which is to support load and usually stationary, the same as trusses, contain at least one multi-force member. For example, member X up to 3 or more forces. Okay, after this, we will look at this. And finally, we have a machine. Okay, at the final part, which is a structure contain moving part like a bulldozer, okay, designed to transmit the modified forces, pliers or something. Okay, three categories of engineering structure. The first one is trusses, frame, and machine, already mentioned before. So we will go for the truss definition first. Okay, the first one is a simple truss. Okay, after this we will look at the simple truss and try to solve this problem. And we have analysis of truss. Okay, so that we have two type. The first one is by using method of joint, and the second one by using method of section. The several trusses available, okay, in, for example, trusses in the KILIA airports, TUDM aircraft hangars, Stadium Bukit Jalil, rooftop, auditorium, KL Centrals, and your houses at Kampong. Okay, before we go through, let us to familiarize with this term. Okay, we have truss member. Okay, member member consists of rod arranged from one or more triangle. So for this example, we have three members consist of we have three joints together to make a triangle. Okay, so we call it three truss member, and then we have a two force member. Okay, a two force member is a body that has forces, and the only forces, no moment, acting on it is in only two location. Okay, and then in order to have a two force member in static equilibrium, the net force of each location, let's say we have FA is equal to FB, must be equal. Okay, opposite direction and same line of action, that's mean co-linear. So if you look at this diagram, you can see several formation of structure, and then there are two forces acting along the same line of action with a different direction and the same magnitude. So this is, we call it a two force member. Okay, before we go through to solve problems, let's see the analysis and design assumption. Okay, when designing both of member and joint of the truss, first, is it necessary to determine the force in each truss member? Okay, the forces in each truss member. This is called the force analysis of truss. Okay, we do some force analysis. There are two assumptions, okay, need to carry it out. The first one, all loads are applied at the joint. Okay, all loads are applied at the joint. So that weight of the truss member is often neglected. That means the weight can be omitted, whereby the weight is usually small as compared to the force support by the members. Okay, the force is very huge if you compare to the weight. So the second one is the member are joined together by smooth pin. This means a smooth pin. This assumption is certified in the most practical cases where the joint are formed by bolting and welding, by looking at this picture. Okay, with these two assumptions, the member act as a two force member. Okay. They are loaded with either tension or compression. That means in the upper diagram we have a compression whereby two forces act opposite of direction. Okay, which means compression takes place, and the second diagram is a tension. Often compressive members are made thicker to prevent buckling. That means the diagram is something like this. When you apply the force from the upper direction, it will bend at the middle. Okay, a truss consists of straight member connecting a joint. Okay, we can see from this diagram, we have joint A, joint C, joint B, joint D. Okay, no member is continuous through a joint. Most structures are made of several trusses joined together to perform a space framework. So we have several triangles from A, C, D, and then we have B, C, D. So these two triangles join together to make a space framework. Each truss carries those loads which act in its plane and may be treated as a two-dimensional structure. Okay, both welded and riveted connections are assumed to be pinned together. So everything in this bolted, welded, or riveted, so we will act as a pin. So we can see from the second picture in the middle, we have a pin, okay, represent by pin. Force acting at the member ends reduced to a single force and no couple. Okay, only two force member are considered here, which is tension and compression, already mentioned before. So when we see the structure is something like this, so the first thing we need to do is to dismember or disassemble the truss and create a free body diagram for each member and pins. So from the figure from the left, attach together, and then we need to dismember to be a free body diagram on the left hand side. Okay, we have three members, okay, which is these members, and we have free forces acting on each member and each point or each pin. This is by using the information from the chapter number 4, which is we have a pin and rollers, so that the reaction from the AY and AX can be represented something like this in the circle, red circle. So for the roof trusses, okay, there are many type of roof trusses, okay, from the regular scissors, cambered, dual pitch, and then we have a many mono pitch, cathedral, attic, okay, and then we have a bridge trusses, Baltimore truss, okay, this one is a bridge, okay, for the bridge, belly truss, camelback truss, okay, and many more. And other type of trusses, okay, we have stadium structure, cantilever portion of a truss, okay. Okay, now we go for the simple trusses, okay, which is a rigid truss, will not collapse under the application of load. A simple truss is connected by successively added two member and one connection to the basic triangle truss. So we have a basic triangle, we have a three force members, okay. And in simple truss, we have these rules. M equal to 2n minus 3, whereby M is a total number of members, N is a numbers of joint. So if you want to determine the value of total number of member, okay, if we have a number of joint, so we can put the number of joint in this equation and we obtain the value of M. Okay, this is the simple trusses, and we have several simple trusses. Here we have a triangle, okay, to be a compound trusses. And for this equation, let's say if you look at this triangle, okay, we have three joint A, B, and C. And if we have this is n number of joint, we have three number of joint, and then we put in this equation 3 times 2 equals 6 minus 3, we have 3. Okay, that's mean we have total number of member is 3. So also we have this diagram. We have 1, 2, 3, 4. 4 number of joints, so we put 4 here. So we have 8 minus 3, we have 5. So we have 5 member, 1, 2, 3, 4, 5. Also in this diagram also you can figure out by yourself. Okay, we will go for the analysis of truss. We have two method. We have method of joint and then we have method of section. Later on we will go for this method, but first we will need to look at the example of the simple trusses. Okay. So this is the example of simple trusses. We have two triangle attached together, okay, in the method of joints. So that the first is we need to dismember the truss and create a free body diagram. So we have 1, 2, 3, 4, 5 members, and we separate it away, and then we produce a free body diagram. And also at the joint A, B, C, and D, we need to produce a free body diagram. So all free body diagram will produce something like this. Okay, the force, the two forces exerted on each member are equal, supposed to be, because of from the Newton's third law, have the same line of action and opposite direction. Forces exerted by a member on a pin or joint at each end are directly along the member and equal and opposite. Okay. And the condition of equilibrium on the pins provide 2n equation for 2n unknowns. For example of thrust, we have 2n equal to m plus 3. Okay, this one basically is from the previous equation. So if you want to obtain the value of m, so if you have the n value, so you will obtain the value of m. Condition for the equilibrium for the entire thrust provide 3 additional equations which are not independent in pin equation. So let's see this kind of structure. So we have 5 members: number 1, number 2, number 3, number 4, and number 5. Okay, so if you can see here, the first members you act as a compression. That means two forces compress, okay, at the opposite direction. This one is a compression. This one also compression. Okay, this one tension, and this one also tension. Okay, this is the assumption that in this diagram, assumption in this diagram. Before we want to, so if you set this one is compression at this member, so this point of C here must be the opposite direction of members number 1. So if you have this force acting this direction, at C supposed to be the opposite direction. If you assume that this is compression from this direction, at point C is a opposite direction, something like this. So at members number 3 is a tension, whereby the force is acting downward. So at point D is opposite direction acting upwards. Okay, this by using the something like this law. Okay, so basically logically, if you apply load, external load to the right here, something like this. Okay, this member is supposed to be what happened. Okay, if this member is tend to be compressed, right? Compressed like this, compressed. Okay, and this member tend to be tension. Okay, so if you don't know how to solve this problem, you will assume that this is in the tension. Okay, so in tension you will put something like this. Okay, at point B you will put the force is something like this. Okay, something like this. Okay, opposite direction of tension. Okay, okay, apply the scalar equation of equilibrium by using this Newton's law, and answer the and also the assist from the moment. So we will compute, and finally we get the result. If the result is positive, that means the direction we assume first is correct. If the answer is negative, that means the force that we assume is wrong, so that you need to change the direction of the force later on. Okay, let's say we go from the problem number 1. Okay, diagram given, we have external load towards the right direction, which is 500 Newton, and then we have 3 members represent the triangle, and then we have a roller, and then we have a pin. So from the question asking for the uh, tension or compression of each members, so that the first thing we need to do is we need to break up into, or these members of this diagram to be 3 members and 3 joint ABC. Okay, actually we have several method, okay, several method to solve this problem. Okay, but the first is I would like to show you a simple method first, and then uh, another method. uh, okay, and for this method, okay, we need to analyze for each joint. Okay, let's see, we have a joint B, we have a here joint B, we have a 2 unknown member force. Okay, from whether uh, you want to make it something like this or something like this. Okay, but if you don't know, okay, you set all 3 members as a tension. But in this case, from the logical, we can see that if we apply external force to the right, this member supposed to be compressed, right? Compressed. So if it will be compressed, okay, and then this also compressed. So at point B, supposed to be this upward direction, this direction, okay, upward direction. So the compression and this upward direction. So we have at point B, the free body diagram is supposed to be 500 to the right, and then force FBC towards the point, and then for the FBA, maybe we don't know. Okay, if we don't know, we put tension. If we know this one, we will put if we know this one, compression or tension, just put there. So if you don't know, you just put tension. From here, maybe from the logical thing, maybe this is a tension. Okay, tension. So here, from the this member tension, so we have upward direction, and for point B, the free body diagram of point B is towards downward. Okay, so we have we only know the known force from the external force, which is 500 Newton, and 2 unknowns, this one and this one, we don't know the value. And for point A and joint A and joint C, or point A, point C, so we will produce free body diagram is something like this and something like this. Okay, so at joint C, we have 2 unknown force. Okay, we have 2 unknown force from SBC, FCA, and we also don't know the reaction force from CY. So we have in total we have 3 forces we don't know. Okay, and at joint A, we have 2 unknowns force member we don't know from FBA and FCA, and two unknown reaction force we don't know, which is AX and AY. Okay, from the information that I have said before, there are many methods to solve this problem, but first we try to look at this simple problem first. This simple problem is not we don't apply the moment, okay, moment, but by using the net force, the Newton's third law, we can easily solve this problem, okay, from this simple question. Okay, so if you don't know the diagram, don't know whether the compression or tension, so it will be making is like diagram number 2, something like this. So you assume all intention, okay, or if you know, you will solve this problem by using diagram number 1. So we will go for diagram number 1 first. So later on we will see the diagram number 2. Okay, you will use a moment. Okay, now by using this kind of uh, simple method, we don't encounter the moment first, but we try to use a third law of Newton's. Okay, so if you find out there is a very difficult to solve by using this technique, you will use the moment methods together with this net force equal to 0. Okay, several methods, okay, including moment, including solving by using a triangle, okay, and uh, Pythagoras theorem or something. Okay, so that's all for this video. Okay, thank you very much.